This is Bob. He is an artificial intelligence engineer. His dream is to build a simulated universe populated with sentient beings. There's not enough computing power to accomplish this. One day, he attends an astronomy seminar where he learns a black hole's gravitational pull is so strong that even light is unable to escape. The radius at which the escape velocity from an object will equal the speed of light is called the event horizon. The force of gravity is a curvature of space and time. The larger the mass of an object, the greater the curvature. Imagine a pool table with a tabletop made of a thin rubber sheet. Upon placing an object onto this tabletop, the rubber sheet will become distorted. When an object with enough mass is placed on the tabletop, the rubber sheet pinches off into a bubble. Trying to play pool, the balls will fall in and will not be able to come out. Similarly, a black hole curves space so much that space falls over on itself. It is important to know black holes do not cruise around space, sucking up everything in sight. Only if an object's orbit takes it too close to the event horizon will it be unable to get out. Anything that crosses the event horizon will need to travel faster than the speed of light to escape. In other words, it is impossible because no other particle can travel faster than light. Light is also affected by the curvature of space and time. Light do not slow down as the speed of light is a constant, but it does lose energy as it works to climb out of a gravitational field. Consequently, to an external observer, the light's wavelength is lengthened as the energy of light is proportional to its frequency. As a result, time will seem to slow down near a black hole to an external observer. Imagine our clock is based on the frequency of the radiation. As the wavelength becomes lengthened, the wave crests are further apart, causing the clock to appear to slow down. This phenomenon is called time dilation. Bob has a brilliant idea. If he travels near a black hole, but not close enough to fall in, his time will pass slower compared to time on Earth. He hopes that upon his return, computers will have advanced to a point where he can finish his research on AI. He hijacks a spacecraft that could travel half the speed of light to search for a black hole. Because even the nearest galaxy is 25,000 light years away, Bob cryogenically freezes his body when he travels between galaxies. To find a black hole, he looks for binary star systems where the invisible member emits large amounts of X-rays. The X-rays are caused by the compression and large acceleration of gases the invisible member attracts from its partner. This suggests the presence of a black hole because the object must be compact with a strong gravitational field. Thus, the invisible member must be a neutron star or a black hole. To determine which it is, the mass must be calculated via the orbital period and velocity of the companion star. The back and forth motion of the spectral lines are observed to determine the orbital period. Doppler shift measurements are used to determine the orbital velocity. The orbital inclination is factored in, and all three variables are related using the mass function and the modified form of Kepler's third law, where k is the velocity, I is the inclination angle, g is the gravitational constant, m is the mass, and p is the orbital period. If the calculated mass is greater than 3 solar masses, the invisible member is a black hole, as neutron stars cannot exceed 3 solar masses, which is a mass limit for which neutron degeneracy pressure can counteract the force of gravity. After years of searching, Bob finds a black hole. He makes the mistake of driving too close to the black hole. The pull of gravity on the front of his body is much stronger than the gravity acting on his back. He is stretched to a point where he's spaghettified. He falls into a black hole where he will never be seen again. Black holes don't exist forever. They evaporate in a process called Hawking radiation. Space is filled with pairs of virtual particles popping into existence and annihilating each other. When this happens near the event horizon, one of the particles crosses the event horizon before it meets and annihilates its partner particle. The other particle is then able to escape and become a real particle. The energy required to create the new particle comes from the black hole. Because energy and mass are equivalent, the black hole must decrease in mass as it radiates. This process is incredibly slow, with some black holes taking up a Google years to evaporate.